Let's begin at the beginning. Uh, the the simplest transport model was done totally classically, and we know it from the Drude's model. The idea was they treated electrons as classical atoms in a gas, like rigid balls. The velocity of them were determined by the classical Maxwell's Boltzmann distribution, which is dependent on the temperature. And the electrons were assumed to be independent of each other other than the collision. And there were some few simplifying assumptions that you have an effective lifetime and such. One can derive the Ohm's law using such assumptions. We can show the Hall effect for and thermal conductivity in a few metals. One can explain why there is a linear relationship between the ratio of uh, thermal conductivity to electrical conductivity with temperature, which we call the Wilhelm-Franz law. With that in place, there had been a lot of difficulty, saying that the most important difficulty was when we take the classical transport model. Root kind of assumed that you have scattering with the atom core. Let's say we have atom cores like this. The electrons were thought to be scattered off the atom cores, but in reality, we know that is not true. Electrons have been known to travel across several unit cells, even at room temperature. At low temperatures, it even goes to uh, several micrometers, which are several thousands, millions of unit cells. So there has been some difficulty in understanding such transport mechanism. And also the fact that atoms and electrons are not, electrons particularly, are not classical bonds. So we go to what is called as a semi-classical transport, where we assume that the electrons do not obey Maxwell's Boltzmann distribution. The energy and the velocities of electrons are not classically determined. There are certain conditions at which the electrons can occupy, given a particular density of states. There is a particular function called the Fermi-Dirac distribution, which tells you what energy level will be occupied and what will not be occupied. This comes about because of what is commonly called as the Pauli's exclusion principle. We will not go into these details, but then because electrons have fermions, they have certain conditions. They cannot have all the quantum numbers the same. So that will make them to have increasingly higher energy levels, irrespective of the temperature that we are talking about. So typical velocities are larger. When the typical velocities are larger than what the temperature determines, obviously the mean scattering lengths are larger. So we are already in the path of explaining why in certain metals we have large mean scattering length. But let's go slowly and then see what sort of how this assumption changes the transport properties. We will include some modifications and something about scattering, something a little bit detailed about scattering. uh, Drew did not deal a lot about what scattering actually means and what really happens, how electrons get scattered. So we will deal a little bit of that today, and we will talk about one scattering principle in detail, and all others we will just wave hands and show that this is the way it can be done. Okay. So before we begin into doing our full transport equations, I thought I will give you a short background. So if you feel that these are all trivial, kindly tell me and I will just jump across. Okay. So this is just so that I bring all of us in the same page. I was not sure what sort of background we will be having. So I just have a few slides. Bear with me if this is too trivial. So a free electron can be expressed in this particular fashion. E power I k r is a traveling wave. And if we have an electron in a periodic potential, we have a solution which is called as a block solution. The reason behind this is a little bit, you have a derivation for this, but we don't have to go there because it is commonly known. The most common solution is of this form, which is psi of k of r is equal to uk of r into e power I k dot r. E power I k dot r is the plane wave. uk of r is a potential or is a prefactor which has the periodicity of the potential. The most basic definition of the block equations comes about like this. If I have a series of atoms and I know about a wave function about one particular atom position, I can guess the wave function at a lattice translation. What I mean by lattice translation is if I take a unit step in which the crystal looks indifferent, then the wave function will just be phase separated from the original one, and the phase is e power I k dot r being the distance that of the jump that you took, right? So the solution of an electron which is in a periodic potential given like this by a block wave, there are certain other conditions which shows you that you cannot have, okay, so already I have assumed that the electrons are waves. Okay, so we have already crossed this. A wave has a wave vector, and there are certain conditions which tells you that you cannot have a continuous distribution of wave vectors and you can have only discrete values. Why that should be true is taken by what is called as the Boltzmann boundary conditions, which say that I take a lattice or I take a sample, it can be taken as some small portion of a large ring. So what I mean is I start at this point and go around this ring. By the end of the sample, I come back to the same position. Now you can always ask, why should this sort of an assumption be true? In the sense that my sample need not be a ring; it can be like a standard bar. The reason behind this is if I have a sample which is just composed of these blue atoms, the smallest k value has the largest wavelength, right? Because they are inversely related. I start at a point. It is just to say that when the sample ends, I should be at the same point once again. Why? Because if it ends at not an integer integral or integer multiple of the wavelength, then I will have reflections of this particular wave, and these reflections will cause interferences and all other uh, uh, consequences of these interferences, and hence it's assumed you do not have interferences of the same particle itself. Now that is something that happens later on, but we don't talk about it right here. So there is a limit on how small a wavelength or how a wave vector that you can have, and that if you show that it follows the Boltzmann boundary conditions, you can say that the smallest k value, smallest delta jump that you can have is 2 pi times the reciprocal lattice vector divided by the number of unit cells that you will have. Once again, I'm not going into too much detail. This is pretty much basic solid state physics, but all I wanted to mention here is that you have k values which are discrete. Once you have discrete k values, it tells you that there is a finite density of states. If the k values are not discrete, of course, you can have infinite number of states in any particular Fermi wave vector. Let's say I have a particular Fermi wave vector which goes from the center of this k space to some point here. If the k values are not discrete, you might have infinite number of states, and hence there is no limit, right? But you have finite number of states that comes about because you have you have the smallest k value that you can have. Once that is given, I take some volume in three-dimensional space, which is given by 4 by 3 pi kf cube. And any small change in the three-dimensional space, I can calculate how much states do I add, which is given by the density of states. It is dg by d. dg is the number of states. dg by d. If I take a small step d, how much density that I add per unit volume of the sample, will turn out in the three-dimensional case to be proportional to the root of the energy that we're talking about. Okay. Now that we have covered these basic aspects, now let us jump into quasi-classical, semi-classical transport, or whatever that we call it. Okay. So we started off with saying that the electrons are not balls, are not classical balls as we spoke before. We have waves which move. So if there is an electric field here, we understand that the electric field will accelerate. What do we mean by accelerate? Is its velocity will keep on increasing, right? So velocity increases, the mass does not apparently change. So the k value starts to increase, right? So basically its momentum value starts to increase, its energy starts to increase. So if I have a field here, I have an electron, it will slowly climb up the dispersion relation. We previously showed that there are there are some discrete k values, and these discrete k values give you these energy values in these points. How do you get these things? Are is by solving the Schrodinger's equation, you get this dispersion relation. Once you have the dispersion relation, if I have a field, then an electron will just slowly gain energy. It will keep rising up, right? How much can it raise? Once again, I don't have the luxury to go through all these in detail, but as it goes closer and closer to the half the brilliant zone k value, it can get scattered. And one can actually prove that the scattering probability with a periodic lattice, it's called as Bragg reflection, is maximum when it can be reflected by the reciprocal lattice vector G, right? So as it slowly goes from here to this point, it gets scattered back to this particular value. This is called as Bragg reflection. This is the case in which you do not have any other property like scattering, right? Now, how do we reconcile the fact that we do not have a particle but a wave? If I have a true traveling wave whose reciprocal space will be a one single delta potential here, not a delta potential, a delta function here, then it's easy to see in real space it extends throughout the space, right? It cannot be thought of like a ball which is localized. So the best way to envision a ball, something which is small, is to have a wave packet of the block waves that we know about, right? So the block waves are basically summations, and now we have summation of a summation, right? Or you have a block wave which is written like this. The wave packet is written by a summation whose coefficients are written in this fashion. So instead of one single delta Dirac delta function in the reciprocal space, now you have a small spread. If I have a Gaussian sort of a spread, you know that if I do a Fourier space, let's say transform, I will have a wave packet which will also have a space corresponding to this particular spread, inversely related to this spread, right? So I will have a wave packet which will spread across a few atomic distances, and this quasi or semi-classical description is valid only if any external field that I am applying is slowly varying in comparison to this wave packet. If this is true, then we can assume that this wave packet behaves almost similarly like a classical ball, right? If it is not true, if you're not talking about wave packets, and if this is infinitely large and your external field varies faster than how the wave packet varies, then we actually cannot have this ball approximation, because very soon we will see that we will take these electrons which are waves to precise, not to precise in the sense that to progress by equations dictated by classical giants like Newton, or in the sense, whatever, if I have to repeat myself, in between scatterings, in between collisions, we will assume that the electrons behave classically in the sense that it follows Newton's equation or Lorentz forces. Okay, in case uh, you have a magnetic field. So before we begin, one also has to ensure that if you have a perfect crystal, that is, you have a potential which is infinitely periodic, a perfect crystal can be shown to be dissipation free. It is not like an electron which is going through some periodic bumps such that its velocity keeps degrading. An electron which is on a perfectly periodic potential will have no dissipation. We will slowly show. If you take a block wave to be described in this particular fashion, one can show that the classical or the conventional momentum operator, which is minus I h cross delta of psi n k, will give you an equation which does not look eigen-like. Right? A typical eigen equation acts like p hat psi is some eigenvalue times psi. Right? Now you have some additional component here. Sorry about that. So what we do is, even though this is not an eigenvector or eigenvalue, we call P is equal to h cross k as a crystal momentum. Now, how do we know a velocity of the block wave? The velocity of block wave can be written as 1 by h cross del k en. Now, why this velocity is true? this velocity is not the phase velocity of a single particle, but then it is a velocity of a collection. It's called as a group velocity, and group velocity is like a dispersion, right? So basically, you have a del k times or a del or a derivative of the energy with respect to the k gives you the group velocity. En is called as the block energy values. Thus, if you have an electron with a particular velocity Vn in a periodic lattice, you see that it does not change and it depends only on the band structure of this material. So for a perfectly periodic crystal which does not have any changes, the velocity becomes a constant value and it is actually dissipationless. It does not decay with time. So a perfectly blocked crystal should have no degradation of the velocity and then has perfect conductance. But that's not what we talk about, right? So that's the least interesting aspect. When we have, so this is the case in which there is no scattering, and the electron will just keep on accelerating, whose velocity and momentum will keep on increasing. As it reaches the zone boundary, it gets scattered back. But what conventionally happens in any normal crystal, the electron starts to accelerate, the velocity starts to increase, the momentum starts to increase. At some point, it gets scattered, and this point where it gets scattered is the quantum aspect that we are going to talk about. Sorry, in between these 2 points, we assume that the electron uh, develops in the classical fashion. We can look at it in the real space transport picture, where let's say we have a free flight. We have an electron in z, can be in any space. It gets scattered, and depending upon the force, it moves. It does not have any knowledge about what happened before. So after the scattering, it moves, and then the direction at which it scatters, we can actually calculate. We'll soon see, depending upon the potential that we have, depending upon the scatterer that we have, we can actually predict what is the maximum probability, or what is the probability of this particular electron which is being incident here to be scattered along a particular direction. That is something that we can see. But once the direction is determined, the way this electron will accelerate again depends purely on the potential that we have, and it will just follow the Newton's equations between the two collisions. So I guess Rick would have probably explained this Boltzmann transport equation before, but I thought because we are going to talk about scattering today, it will not hurt us to take a look at the scattering phenomena a little bit like from a top level. So let's say that I have a 6-7 dimensional phase space, in the sense I have 3-dimensional space, I have 3-dimensional momentum, and the time that we have, right? And in the 7-dimensional phase space, a particle is kind of moving, and at some point r, at time, let's say del t, I'm asking what is the probability for this electron to be. The most simplest answer would be, what is the probability of an electron at a previous place in time, which is time shifted by del t, right? So basically, this r minus del t vk will be this empty space. If you know the probability of occupation at time t equal to 0, and if no other activity happens, it's easy to see that, because we know that the velocity is in this particular direction, or in whatever in the 7-dimensional space that we're talking about, we can tell that what is the probability of an electron to be at this particular space at time t equal to del t. Once this equation is known, we can actually write that if we can bring one from the other, we can bring it down and then divide it by del t. If the time scale is small enough, we call this df of k by dt equal to 0. Now this is the Boltzmann transport equation, because from here you can see that we can divide this solid differential into a lot of partial differentials. The first one being the time derivative, and the second one, you have a small derivative of the Fermi function with respect to the position and how slowly the position changes with time. The same thing you can write of the Fermi function change with the momentum p, and how the momentum changes with time, right? The summation of all these things will tell you how the Fermi function totally changed with time. And if we know del r by del t to be the velocity, now the first part is basically uh, is del times fp, fk. and del P by del T is the force that acts. Right? This is the classical Newton's change in momentum with the Newton's first law. So you have the force times del P. Del P is the gradient with respect to the momentum times uh, the Fermi function. Now we have not assumed, sorry, we have assumed that there are no generation in the sense that you do not generate particles by, let's say you have electromagnetic radiation which generates, or you do not have electrons and holes which recombine. So these two are not particle number conserving. Once you start to have non-particle number conserving components, then things start to get a little bit more tricky. But for our easiest cases, we'll assume there are no generation, there are no recombination. And in thermodynamic equilibrium, you will obviously have dfk by dt to be 0. Now, so the previous case, we did not assume any sort of mechanisms in which you have an electron which gets scattered in or scattered out. What I mean by scattered in or scattered out is you have an electron which is moving with a particular momentum p. There is a probability of this particular momentum to be changed to p dash. Either you have an electron which had a momentum p dash in the first case and then got scattered into p, or you have an electron with momentum p and got scattered out to p dash. So in case if you include scattering into the Boltzmann's equation, you can write that the change in the occupational probability of the electron with a wave vector k can be given by an addition of an electron which scattered in minus an electron which scattered out. So here we use an approximation tau m, which kind of pushes a lot of things under the rug. We will deal with one such thing in detail today. So this tau m is called as the characteristic lifetime or momentum relaxation time. One can actually calculate this if you know what is the most dominant scattering behavior, and that's something that we will talk about today. There are various types of scatterings that is typically observed. The most common one being the impurity scattering in semiconductors, because we almost always have dopants when we use semiconductors. And when we have dopants, you'll have scattering from the dopant ions which degrade mobility. This is a cause of concern in most semiconducting materials, in nanostructures, in the let's say in heterojunctions and such. You always have lattice vibrations or phonons scattering from lattice vibrations or phonons. You have surface roughness, you have alloy, you have electromagnetic interactions in the sense that you shine some photon, you have some electromagnetic interactions. In addition to this, you have carrier scattering. So you have an electron scattering, electron hole scattering. You can have electron quasi-particle scattering and so on. In general, any sort of inhomogeneity in the periodic potential will cause scattering, because as we saw previously, if you have a completely homogeneous potential, it should not scatter anything, right? So basically you should have infinite conductivity. Many times we do not have infinite conductivity because the mobility is not infinite, because we have imperfections, and we will see what happens if we have imperfections. So most of our work when we try to study conductance can be broken down into these steps. One is we have to identify what is the most dominant scatterer. If you are not able to identify the most dominant scatterer, you are probably in a fix. So what you have to do is you have to go back and calculate all the scatterers that you know about, and you can never be sure if you are complete. So the easiest way is to say that you have one most dominant or two most dominant scatterers, and then try to compute what is the scattering rate. You compute what is the scattering rate. The scattering rate does not necessarily have to be a momentum relaxation. Each scattering does not really have to relate with momentum relaxation. Some of these scatterers do not relax the momentum so quickly as the others. So one can actually estimate how quickly the momentum relaxes. And from there, you can calculate what is the mean free path. You know the velocity, you know the scattering time. You can tell what is the distance an electron goes before it gets scattered. There are a few kind of, most of these scatterers can be put into big baskets. If I have an electron which comes in with a momentum p into a scatterer, it gets scattered to p dash. There are two possibilities. This P dash can be associated with an electron which has the same energy as the electron which came in. Then we call it as an elastic scattering. This is from probably high school physics, right? If the energies are different, we call it the inelastic scattering. There are a few examples. You have impurity, alloy, and defects mostly causing elastic scattering. You have phonons, electromagnetic interactions. You can have electron carrier scattering, all of them having inelastic kind of relationship. When you have an elastic scattering, the mean scattering lifetime tau m typically depends upon how many possible uh, states that you can have. So df is the density of states with momentum p dash. So in a material, you have particular dispersion, you have a density of states which depends upon the k value. So the time at which it takes to scatter depends upon how many possible states that you can have, right? And wp p dash gives you what is the scattering rate. You must have seen this from Fermi golden rule. I suppose Rick could have dealt with Fermi golden rule. So we can calculate what is the rate at which the electron occupation probability f changes. It is given, as we saw previously, the incoming scatterers, which is f of p dash, the occupational probability of electron with p dash, and the scattering probability from p dash to p. And now you integrate this with over all possible p dashes, right? Minus, you have the occupational probability of electron at p, and then the scattering probability from p to p dash. And now again you integrate this to all possible p dashes around the area that we're talking about, right? So this is the way in which you calculate what is the change in the occupational probability. Now, when we talk about an inelastic scattering method, here we have a fix. We can come to this particular region where it is the same, but in the elastic case, it's easy to see that the scattering probability of p dash to p should be same as p to p dash, because there has to be microscopic irreversibility between states which have the same energy, right? Once this is true, then the scattering probability, scattering rate can be written in this particular fashion, which is the simplified case. But if you have an if you're talking about cases in which you do not have energy, I mean you have energy losses or you gain energy, in sense that you do not have particle number conservation, in the sense you have phonons which are absorbed or emitted, then you need to do a little bit more, because we need to calculate, or we need to know the relationship between the various scattering rates. That is, w is the scattering rate from p dash to p, and wp p dash, right? How do we find this? At equilibrium, we can always say that what is the probability, that is, there is no net change in occupation in all these states, right? You are at thermal equilibrium, nothing changes at this particular. There are changes, but there is no net change over infinite time. So once you know this relation to be true, you can calculate what is the relative scattering probabilities or scattering rates from p dash to p and p dash is given by f naught p. F naught is the equilibrium occupation probability of p, and equilibrium occupation probability of p dash. Once this is true, we can calculate this using this particular expression. All right. Okay. So here I have it. All right. So we crossed here. Now we are in this. Now we are ready to handle ionized impurity scattering, right? So we saw how do we. So basically, in the previous case, we saw how we can derive at one governing equation, whether you have an elastic scattering scatterer or an inelastic scatterer like phonons, or you have elastic scatterers like defects or impurities. There is this governing equation which can help you to finally calculate what is the rate at which they scatter. And for that, the most important component is W. W is the scattering rate, WP dot P dash comma P, or P to P dash. And the way to calculate this is by using the Fermi golden rule. There are some conditions that we will slowly derive, because let's say if you're talking about an ionized impurity, this is very much essential to to understand transport in any semiconductor, because in most cases we always have a dopant, and we have a dopant which is ionized, and these ionized dopants are charge centers, right? And these charge centers typically is scattered. So one always wants to know what happens when you have such situations. Let's assume that you have some density of ionized dopants, which is here given as rho, but then it should not be rho, it is rho underscore E. I'm just mentioning here it should be rho underscore E, because as we proceed, as you also see here, it has to be rho underscore E or rho underscore external, EXT. If we have something like this, the potential faced by an electron due to this charge density, let's say I have an electron here in the substrate somewhere coming close to this dopant density, the potential that it faces depends inversely on the distance r, directly on the density of the charge here, inversely related to the dielectric constant epsilon. This is very essential because this dielectric constant epsilon tells you how strongly the potential dies. Right? If you have a very small dielectric constant like air, you can see that the potential goes farther. If you have a very high dielectric constant, you can see that the potential will die quickly. This is already telling you something about what sort of a material that you need when you are talking about transport in semiconductors. You typically want a material with a strong dielectric constant, because you can see that the potential dies much quickly. The impact of this charge density on the electron is smaller when you have something like this. But beyond this particular aspect, now let us go. What happens? Let us go and see what happens. In a typical metal or a semiconductor, you also have some background electronic charge, right? If I introduce a positive potential here, the positive potential will start attracting these electrons in the background, and it will change the way in which uh, the electrons are distributed in this material, right? So what we have is we have a charge density which is external, which is rho e. We have an induced charge density which is rho I. So the total charge density can be written as rho is rho I plus rho e. Right? It's a simple arithmetic, vector arithmetic, right? You have to also include about the sign of these charges. I should not say vector; it is just sign arithmetic. In addition to that, you also have a potential. So I have mentioned the total charge as rho and the total potential as psi. The total potential is a signed summation of the induced potential plus the external potential due to this external charge rho. But you know that from the classic electromagnetic theory, the dielectric response to an impurity that you have added is expressed as rho of k. I will soon show what k is. So k is the reciprocal space or a Fourier expansion coefficient of all these things. The response depends upon the Fourier coefficient, is given by this expression, which is rho e, which is the induced charge density, by the total charge density rho. This is the way in which the material responds to the induced charge density. Whatever, let's say you have a dopant or whatever that you have, because of the induced charge density, you have a total charge density rho, right? So this induced charge density can be always written as rho total minus this is the external and the induced, right? I'm sorry about confusing the names. Let me write it again here, right? So I'm going to annotate. So what I mean is rho I is induced and rho E is external. So this rho E here, what I mean is the external charge density. That is what the dopant density that I have introduced. Clear, close. Sorry, yeah. Rho E is the external and rho I is induced. So this rho E can be written as rho total or rho minus the induced charge density, and finally it will come out to be 1 minus rho I by rho. So the important problem that we have to see is how the dielectric responses to this external charge density is to find what is the induced charge density. So how do we calculate induced charge density? We use Fourier expansions. So this is the simple Fourier expansion. So the external charge density rho e of r is written by some Fourier coefficient times this plane waves. You can write similar Fourier expansions for the total charge density rho, total potential psi, induced potential psi I, and the external potential psi e. Once again, external potential, what we mean is the potential due to the charge density that I've introduced. And why we use this is when we use the Poisson's equation, which will finally relate the charge density to the potential, it's much easier when we have this Fourier expansions, right? Because when you have del square psi, it's easy to see that the case comes out. So the Poisson's equation is written by this: del square psi is minus rho by e. And when we use one of these Fourier expansions, let's say if I talk about the potential psi k, del square psi k will give me k square psi k is minus rho of k by e. E being the static dielectric constant. Remember, this is static dielectric constant and this is the dielectric response. These are little different. So now we derive what is called as the Fermi screening. So the induced charge density due to this external charge, which is called as rho I, is the excess charge in the material due to the potential induced from the impurity, right? So what we mean is I induce some impurity here, and this induced charge density rho is a response of the material due to this external charge density, right? So this rho I is an excess charge density over and above the background. The blue one is the background. You have an additional electron concentration here in the orange region over and above this background. So that is this rho I. So this rho I is some charge Q, is electronic charge, plus N is the electron density, which is Fermi distributed, right? This is some function which depends upon temperature and the chemical potential mu. Because of the fact that you have additional electrons near, because of the induced charge density, you have a chemical potential which is enhanced by this potential psi, right? So the induced is basically you have an enhanced electron distribution, n of mu plus q psi minus n of mu. This is the background and this is the additional one. So the additional charge density is just expressed as a Fermi-Dirac distribution plus some additional chemical potential here, right? So once we have something like this, if we take this potential to be small enough, then we can expand this in the Taylor series expansion, which will slowly come out to be rho I is minus q square, psi being the potential, dou n by dou mu. This is by far one of the most important thing to know is the induced charge density depends upon how much your electronic charge density will change if you slowly pump up the chemical potential, right? It has to do with the density of states that you have, the temperature at which you work, and all those things. It is this which will finally determine how your charge density or impurities change the way in which electrons scatter in the semiconducting material. Okay, so now that we have rho I, we can calculate the dielectric response. There is epsilon of q is 1 plus. So if you see here, it is 1 minus rho I by rho. This is once again minus, so you will get 1 plus q times, q is electronic charge, q times dou n by dou mu by epsilon k square. And if we mark this q square dou n by dou mu by epsilon as lambda square, which is called as the Thomas Fermi dielectric constant, not dielectric constant, it is screening constant lambda. The total dielectric response epsilon k is written as 1 plus lambda square by k square. Now, if we take an example of a point source instead of a distribution that we saw previously, if we take the external charge density to be a point source, the point source as a Fourier expansion as a constant line, right? So rho e of k will turn out to be just q, and the potential is q by epsilon k. If we substitute this, the total potential will turn out to be in the Fourier space by q by epsilon k square plus lambda square. This is just a little bit of math, okay? Now one can actually invert this Fourier series or Fourier transform, and then you get the potential in real space. The inversion should happen in three-dimensional k space, which when you invert in spherical coordinates, you will get actually q by 4 pi epsilon r into e power minus del r. What it means is, if you have a bare potential which decays as 1 by r, when you have a screened potential, what do we mean by screened potential is, if you have a floating or a free electronic charge density, it will start to screen the impurity that you have added. And this floating charge density, what it does, it makes the potential to die exponentially faster. So instead of dying in this fashion, which is 1 by r fashion, the potential energy will now die e power minus lambda r by r. So it will die much faster, much quicker than the case in which you have an unscreened potential, right? So the effect of background charge is to screen the impurity potential from the 1 by r dependence to an exponential decay, in addition to 1 by r, of course. So now let us take an example and then calculate what would be the scattering rate. So let's look at just dopants in a semiconductor. And let's say that there is some fraction of impurities are ionized. And if each dopant provides Ze depending upon the valence amount of charge, the screening potential due to a single dopant is Ze square. This is the total charge that as we described here. So this is the potential. Q is the charge. So you have Ze square by 4 pi epsilon r into e power minus del r, right? E power minus lambda into r. To calculate the scattering matrix due to this impurity, let's assume a plane wave, which is e power I k dot r. The probability to scatter from wave vector k to k prime is proportional to the scattering matrix element. And how do we calculate the scattering matrix element? We calculate what is the overlap function, right? If you take this u of r to be a small perturbation, you add the perturbation on the original wave function and then calculate the overlap integral, which is psi k dash, and do this overlap integral. And how do we do this? We can do this in the spherical coordinates. Once again, if we substitute this e power I k dot r into this, we get this particular integral for this m k k dash. And here we assume that we are going to talk about only elastic scattering, in the sense that k and k dash have similar energies. If this is the vector of k, we assume the k dash is in this particular angle. It is written in this fashion, but it can also be written in this way, right? Starting from here, it goes here. The angle between k and k prime is written as theta, because it is finally this theta which is going to determine what is the probability. And when we calculate m, I'm not going to go through the math. You can see that this m k k prime will turn out to be Ze square, turn out to be proportional to the charge density, V being the volume, E being the epsilon, epsilon being the electric constant, 1 by 4 k square, k being the wave vector of the initial electron, into sine square theta by 2 plus lambda square. And the scattering rate, obviously by the Fermi golden rule, will be square of this scattering matrix element, right? Times delta Ek minus Ek prime. This is the crux of the Fermi golden rule, which tells you that the scattering probability is maximum when you have energies which are similar. Once we know what is the scattering rate, there are a few comments that one can come to, right? In this equation, if lambda, that is the screening constant, is small, in the sense that the electrons do not screen, you do not have sufficient number of electrons in the material. Let's say you have an insulator. An insulator does not have a lot of free carriers, right? So it does not screen so well. If lambda is small, or if the screening is poor, then the scattering rate is proportional to 1 by 4 k square into sine square theta by 2, right? So the scattering rate goes like this. This is wk comma k prime versus theta. It's easy to see that the scattering rate is maximum close to the 0 theta. What we mean is theta is 0. That means k and k prime are almost in the same direction. So the maximum scattering probability is in the same direction in which the electron moves. And as the angle is increased, you have very small probability to be scattered over large angles. This is the case in which you have very poor screening. When you have a very large screening, that is when lambda is extremely large, obviously you can see this lambda square will dominate the sine square. Under such situations, the scattering rate is proportional to 1 by lambda power 4, which is a constant, right? It depends upon the material. So you will have, when you have strong screening, it is not angle dependent. It is not dependent on K. It depends on nothing. It just depends upon the material parameters. So when you have strong screening, the scattering rate is a constant. When you have a weak screening, you have maximum probability to be scattered along the direction in which the electron moves. So it's easy to see that its momentum coherence times will be large, right? So basically, if you have a poor scattering, poor screening, the electrons most probably will move in the straight line in comparison to the other case. Now that we have calculated W, we can go back and calculate what is the relaxation time. Probably Rick would have shown you this at some point. So the relaxation time can be calculated by going back to the Boltzmann's equation. So del F by del T is given by F of K prime minus F of K into this equation. We can actually substitute F of K prime as F of naught, which is equilibrium distribution, plus GK, which is a small change over this equilibrium distribution. And we substitute into this, you get this Boltzmann's equation here, F being the external force that is being applied. The relaxation time is given by this expression, because this is how we have basically defined the relaxation time tau. If we go back to our previous slides, GK was basically written as delta, small delta F, but it is just a small nomenclature change. So when we rearrange this equation, we get 1 by tau, which is the relaxation time constant, is written by Wk comma K prime. Vk minus Vk prime, this is the velocity, right? And the orientation of this velocity times dot F, that is what is the direction in which the force exists, and what is the change in the velocity between K and K prime. So this is the total integral, and upon this dot product is what determines upon this dot product is what depends the mean lifetime tau. It can easily be explained by this particular diagram. You have K along Z, you have K prime. Let's say the angle between the force and K prime is written as theta and theta dash. All we worry about is this alpha, which is the direction between K and K prime. So the relaxation time constant 1 by tau is written as integral W of K comma K prime times 1 minus cos alpha dk prime. So I'm not going into the details about derivation of this. Probably you can find this in standard textbooks. So once this is given, I substitute this W of K minus K prime, and then one can actually get back to the value of tau. And once you know tau, you can calculate what is the mobility. And the mobility turns out to be my E times tau by m star. When we work with impurities or charge impurities, it can be seen that the mobility goes as T power 3 by 2. This is an important aspect when we talk about charged impurities. What it means is the mobility degrades as you reduce the temperature, or you have a mobility which improves as the temperature increases. This can be contrasted with other traditional scatterers like phonons, where as temperature reduces, the mobility typically increases, right? One can also look at a different way in which this can be expressed. Like if you have a larger temperature, you have electrons which are moving a little bit faster. An electron which is moving a little bit faster is relatively less affected by an impurity in comparison to an electron which is moving a little bit slower, right? So these are different ways in which you can look at it. Now that we have seen impurity scattering in a little bit detail, I will quickly run through some of the other examples. So you can have scatterings from alloy. Let's say you have an alloy of two materials A and B. When we have an alloy of two materials A and B, each of the lattice point can have random you can have a random probability of the lattice point being occupied by A or B. And let's say that A and B oscillates like this, and A and B have different ionic potentials. The total potential can be written as x UA plus 1 minus x UB. Here x is the alloy concentration, in the sense we have AX plus B1 minus X kind of an alloy. Okay. You can take you can take A to be indium and B to be gallium in an InGaAs material, so to speak. The typical approximation that people take when they talk about alloy scattering is you take the scattering potential to be like a hard sphere and affecting only interatomic distances. This is how this is conventionally taken. It is the most easiest to handle. Whether this is true everywhere or not, we do not really know. Many a times we know that this works approximately, but one has to look at it closely for each application. Alloys are something which is very hard to predict. Okay, this is just one such example. Del U is written as just U not a constant because it's a hard sphere which works only when the distance is smaller than the interatomic distance R naught. If this is the case, we can use the Fermi-Golden rule, which tells the total scattering probability is 2 pi by h cross summation over all k primes, m the scattering rate of k prime into del ek minus ek prime, and m is written by e power I k minus k prime. This is the overlap integral into del u, right? And del u we assume to be a constant. And if this r is very small, we can assume the overlap to be 1. And you will have 4 pi by r cube, that is a sphere, times u naught. With this, you can once again substitute this m in this w, you get some scattering. Now, this is just an example to show how this can be calculated. I'm sure when you have to do it specifically for one particular application, these potentials have to be changed. In addition to this alloy scattering, you also have carrier scattering. What do we mean by carrier scattering? Is if I have an electron at K1 and I have a hole at K2, you can have both the electrons and holes influencing each other such that the electron gets scattered from K1 to K1 prime, and you have the hole getting scattered from K2 to K2 prime. When it happens, it can happen in two different ways. One is called as a direct way, in which the spin states do not change. In which the spin states do not change and K1 gets scattered to K1 and K2 gets scattered to K2 prime. In the exchange situation, the spin states do not change, but K1 gets scattered to K2 prime, right? So basically here you see the electron gets exchanged to a hole. It's called as an exchange scattering. These are all different probabilities that for it to happen, right? You can think of this as this electron getting recombined and getting scattered, and this hole getting excited and getting scattered. Whether how it exactly happens, because this is going to be a second order process, is not yet clear, and you don't really have to know. But these are just probabilities of various scattering events. In addition to the spin not being changed, you can also have a scattering situation in which the spin changes. So K1 gets scattered to K1 with the same spin, or K1 gets scattered to K1 gets scattered to K1 prime with an opposite spin. Right. So these are the two different ways in which the electron scattering can happen. Now that we have seen some theory, let me very quickly cover some basics about some basic use of these scattering theories in practical examples. So I suppose all of you must know about layered materials. There are a bunch of layered materials. Layered materials are different, have some different classifications. One, you have elemental layered materials like graphene, silicene, arsine, stannine, I don't know, galenine. There are so many such atomic layered materials. And you have black phosphorus, which is a direct band gap semiconductor. You have transition metal dichalcogenides, which are also direct band gap in the monolayer limit, but you have them to turn to an indirect band gap semiconductor in multi-layers. You have tin selenide, tungsten selenide, and so on and so forth. But the topic of interest today will be graphene, because it has been studied pretty widely. And the most important aspect of this is it has a linear dispersion in comparison to what we saw previously, where you have a parabolic dispersion. You have a linear dispersion in graphene. The linear dispersion comes about because you have two sublattices which belong to the same carbon atom. So when you do the tight binding approximation for this, it will turn out that you will have a linear relationship between the energy and the K vector. It has several properties. It has high mechanical strength, it has impermeability to helium, and it has high mobility and so on and so forth. But the most important problem is how do you control defects in this graphene. So basically, in my PhD, we did some studies on growth of this graphene, and then we showed that there are ways in which you can control the defects in graphene. And defects in graphene act as charge centers because you do not have dopants, but the defects are regions in which atoms are missing. When you have atoms that are missing, then basically they are charge centers because you have dangling bonds. So the most important aspect when we study graphene is to see how the channel resistance varies when you change the gate voltage. This is something that they do with the people typically fabricate a MOSFET and then they change the gate voltage and then see how the channel resistance changes. This is one simplest way to actually extract mobility. However, there is a question of what would be the most suitable substrate for graphene. There are different substrates which have been explored, which is silicon dioxide, aluminum nitride, aluminum, hafnium, zirconia, silicon carbide, and such. The most important question that one asks is how does these substrates change the way electron and hole transports in graphene, right? So it is for that that we use our Boltzmann transport and the semi-classical transport that we discussed today. So here I have actually fabricated a graphene channel on two different substrates. The substrate is here. This slightly darker contrast is a metal pad, and this really dark contrast is graphene. And you have graphene on top of this dielectric. As I said previously, I have silicon dioxide and aluminum nitride. When I have these materials, I study what is the drain source current at different gate source voltages. I get this butterfly curves, okay, and from here one can extract the mobility by two different methods. One is called as a direct transconductance model, where the mobility is given by GM. GM is the transconductance by length over width of the channel. VDS is the potential of the drain to source voltage, and CG is the gate oxide. As we all know, CG is normalized to area, so it's epsilon by Tox. Yeah, another way to extract mobility is called as the Drude constant mobility model. So what they do is you assume that there is some intrinsic carrier density N naught, and you use this capacitance model to get the additional charge density. And once you know, the total channel resistance is given by the contact resistance plus the Drude resistivity, right? 1 by N mu N. That kind of a way you can actually get what is the channel resistance. So once you know the channel resistance, you get what is the mobility. So what we did is we measured, we took this sample, right, and measured the mobility, the electron and hole mobility at different temperatures. The electron mobility is basically taking this guy and biasing it here. Hole mobility is taking the graphene and biasing it here, right? You are either in the conduction band or in the valence band. And that's what we have done. So we take the field effect mobility and compare between graphene on silicon dioxide and graphene on aluminum nitride. So here I compare the mobility between graphene, hole mobility between silicon dioxide and aluminum. You can clearly see that the aluminum nitride behaves weird in comparison to silicon, right? The silicon mobility now just increases as you reduce temperature. Electron and hole both behaves in the same way. But aluminum nitride has a non-monotonic dependence. As the temperature reduces, the mobility slowly increases initially and then drops drastically. Whereas for holes in aluminum nitride, nothing really happens. It's almost flat. So how do you explain this? For this, obviously you have to go to the Boltzmann transport. So we expressed the total conductivity in this fashion. So this is the Boltzmann's mobility calculation machine, right? Del F by dou E. And this tau, sorry, del F by dou F by dou E is the change in the Fermi distribution with energy. And this tau total is the total mobility calculated from various scattering events. D of E is the density of states. D of E into del F by dou E tells you how much electron get changed, right? When you change the energy. Vf is the Fermi velocity. The total scattering rate total is written as a Matheson's sum of impurity scattering, acoustic phonon, and surface optical phonon. In graphene, these three are known to be the most dominant. As I said previously, one has to know this for a particular system, otherwise there is a huge variety of sources. Once you know this, the impurity scattering is given by this particular equation. We saw this, if you remember, for impurity. The optical phonon is a little bit more complicated, but we are not dealing with phonons today, so I did not go into this large equation. Similarly, you can write for acoustic. So this is not optical, it's once again acoustic. Once I know all these things, I put the values into this equation and then calculate conductivity. And then I can see that I can, the scattering rate or the most dominant scatterer depends which one is the smallest mobility, right? When you have the Matheson's rule, the smallest component dominates because it is inverse. So the mobility which is determined by the surface optical phonons, basically as temperature reduces, it no longer becomes dominant, right? Because it is the highest value. The Coulombic or the impurity scattering reduces as temperature reduces, as we saw previously, and starts to dominate at lower temperatures, which is seen almost everywhere, right? But then for aluminum nitride, for holes, this is the most dominant, but even this does not figure. Why? It is because of the fact that aluminum nitride is polar. So when the aluminum nitride is polar, it tends to attract more charge carriers, and particularly it used to attract a lot of holes, as we saw in our measurements. We always had a lot of holes. So when you have a lot of charge carriers, it will screen much effectively than silicon dioxide. So in the regions where you have a hole transport, hole based transport, a hole dominant transport, temperature largely does not change anything and the mobility is almost fixed. But whereas for an electron, as it because you have a polar nature of the aluminum nitride, it behaves differently for holes and electrons. Electron charge density is much lower than the hole charge density of graphene and aluminum nitride. Because the charge density is lower for because the electron charge density is lower in aluminum nitride, you see a strong Coulombic dependence at lower temperatures, right? So the mobility slowly increases as the temperature is lowered because the optical phonons are now getting lost. After a particular temperature, the Coulombic contributions dominate, and you will see a reduction in the mobility at lower temperatures, right? So with this, I stop. I'll just give you a small recap. We started off with some basic solid state physics, and then we came to the derivation of Boltzmann transport. And then we showed that once you start introducing all sorts of scattering events, one has to know what sort of scattering dominates under which region. And once you know these things, you do some measurements, you can start to tell what sort of transport you can expect, particularly for low dimensional materials and 2D materials. Boltzmann transport happens to be a very useful tool. So with this, I thank you for the opportunity and can take any questions that you might have.